All right, so today we'll have Nishad Maskara from the Working Group telling us about how to enhance the detection of topological order using local error correction. All right, go ahead, Nishad.
Hey everyone, excited to talk to you today, and thanks Arkin for the invitation. So let me share my screen and then you guys can tell me if you can see things.
Yep, looks all good.
Can you still see it?
Yeah.
Okay, cool. So I'll talk to you guys about some of our recent work on using ideas from quantum error correction to actually improve the detection of topological order, in particular with the focus on like topological order arising kind of in realistic systems. So before we kind of dive into the details of our project, I want to kind of quickly motivate, some of the reasons why we want to study topological phases of matter. So for your guys' group, this is probably something you're all very familiar with. But some of the like very interesting features of topologically ordered phases are, that they're kind of stable against arbitrary local perturbations. And like from a physics standpoint, they actually are like very interesting phases of matter. In particular, they have like emergent gauge fields. And because these are also 2D models, they also have anionic excitations. So these are quasi-particles which have non-trivial mutual statistics. And something I'm always kind of in awe about in, for example, in like the toric code, is that from like systems, with just like bosonic degrees of freedom, you can even get things like fermionic quasi-particle excitations. So the properties of these phases of matter are really quite interesting from a physics standpoint. And, kind of more recently, people have also been using topologically ordered states of matter and like kind of thinking about them in the context of error-corrected quantum computation. So, remarkably, we're living in a very special time because like people are actually starting to like realize topologically ordered phases of matter in the lab in, highly programmable, very controllable ways. This experiment here was also kind of done in the experimental part of our group recently, where they realized like a resonating valence bond state. So we'll kind of talk about this experiment a little bit during the talk today as well. Okay, so I guess actually here I'll also pause and just mention that if anyone has any questions, like please feel free to just interrupt and stop me. Arkin said it's also like an informal discussion a little bit, so like please don't hesitate. Okay, cool. So the kind of question that I'll be trying to answer today is how do we detect topological order in like some experimentally prepared state? So to try to phrase the question a little bit more carefully, let's consider the problem of verifying a quantum phase of matter. So if we're given some many-body state and some unknown if we're given some like unknown many-body state, we can ask the question, does this state belong to a particular phase? In order to determine this, we kind of imagine doing different types of processing on the state. It could be quantum processing, or it could be classical processing, or some combination of the two. And in the end, we kind of want to output like a classification, so a 1 or a 0 that tells us whether or not the system is in the right phase. And one of the key figures of merit is the so-called sample complexity. Essentially, it tells us how many runs of the experiment, how many measurements do we need to make before we can make our classification with high confidence. So topological order is like an especially challenging situation for quantum phase verification because like the typical order parameter that people measure, the Wilson loop, actually like decays exponentially. So we'll see this a little bit in a second, but as a result, it actually has very high sample complexity. So today, the way we're going to kind of try to phrase our approach is that it allows us to address this problem of high sample complexity. Okay, so any questions so far? All right, so let's keep going. So today I'll kind of go through this and talk about, 4 different parts of this project. First, I'll give some background, then I'll explain the approach that we develop, and then I'll provide some, interesting applications to novel contexts. And lastly, I'll explain a little bit our theoretical understanding of our approach. So just to give some quick background, a very important toy example, which we're going to study extensively, is the toric code. So the toric code Hamiltonian consists of a lattice where qubits live on the links of the square lattice, And it has two different types of terms, one living on the vertex, the other living on the plaquette. Now, the ground state of this system is composed of essentially a superposition over all loop configurations. So you can think about a loop as being occupied or unoccupied, depending on whether it's in the plus state or the minus state. And the toric code ground state is an equal weight superposition over all loop operations, all valid closed loop configurations. Furthermore, the excitations of the toric code are some of these anionic excitations, which I mentioned earlier. If you take a string of X operators and apply them to part of the system, you'll see that it'll flip the value of the stabilizer, which lives on the plaquette, and therefore costs some energy. And the way you can see that it flips the value is that it anti-commutes with the stabilizer at an odd number of sites, one site. Similarly, a string of Z operators creates an E anion because it anti-commutes with the X stabilizers. Even more importantly, if you actually take an M anion and wind it around a Z anion, which you can kind of see that's a little bit like what a stabilizer does, it essentially drags an X anion through the lattice around the E anion, this picks up a -1 phase. So this E particle and this M particle together have like -1 mutual statistics. And it's these non-trivial mutual statistics that are one of the consequences of topological order. Now, typically, one of the ways that people try to measure topological order in the ground state is by measuring the the equivalent of the Gauss law operator. In this topological phase, which is a Z2 topological phase, the Gauss law corresponds to closed loops, which are, either closed Z loops or closed X loops. And, this condition that I mentioned earlier, that the ground state is composed of, liquid of all closed loop configurations, implies that this Wilson loop operator should always be +1 in the ground state. Or in other words, there should be no excitations enclosed. So these Wilson loop operators are the things that people typically talk about as the order parameters of these systems. So, so far I've just discussed like the toric code part of the Hamiltonian. However, in realistic systems, you can also have perturbations. And in particular, we can imagine both like transverse or longitudinal perturbations along the X or Z direction. Now, topological order remarkably is robust to arbitrary local perturbations, but nevertheless, these perturbations induce virtual fluctuations in the ground state. So in perturbation theory, they can essentially lead to like some finite density of local anion pairs in the ground state. And the way that this manifests itself is that if you measure like a short open loop, you'll have non-zero expectation value. If you have like finite value of hx or hz. However, the topological phase, which is supposed to be the phase where Wilson loops are close to 1 and the number of anions is very low, survives for like a finite amount of hz and hx perturbation. And the reason is that if you look at if you're trying to characterize the topological order in the phase, you really need to look at like long operators. So either long closed loop operators or long open string operators. And if you want the long X open string or Z open string operators to be non-zero, you actually need to leave the topological phase. So if you actually apply like a large enough perturbation along X or Z, you'll eventually leave the topological phase, and these open strings, which kind of measure, which create and annihilate anions at their endpoints, will become non-zero. However, as long as you remain in the topological phase, the thing that will be non-zero are the closed loops, the Gauss law operators, which essentially measure large regions and tell you that there's no enclosed charge, no anions. Okay, so any questions on kind of the toric code plus the magnetic field and like the different kind of behavior that we're going to see?
So,
okay.
Sorry, those open loop order parameters, those are like the disorder parameters for some Ising type model, right? And does that mean they change smoothly as you go around the outside? I mean, there should be some long open string that's non-zero all the way to the outside of that phase diagram. Is that correct?
Yeah, okay, so that's a really good question. So you're essentially, okay, so if we like imagine making hx really large, then here, you know, the system is essentially just going to be like a state that's polarized along plus everywhere. And there you can kind of see that like long x open loops will be non-zero. And you're kind of asking now, like, what if we move smoothly from like here, you know, all the way down here, where now like long z open loops will be like non-zero because the state will be polarized along up. Indeed, you can do this smoothly, but kind of in the middle, you know, the loop that you're going to be measuring isn't like an x string or a z string. It's actually like a string of like y's, you know? So I think the statement is that there is a long open string that remains non-zero, but it's not necessarily in the same basis as the one at the kind of like, you know, fixed points here and there. Actually, this idea that there's always kind of like, you know, a version of the order parameter that is smoothly connected within a phase is actually going to be super important when we discuss our like error correction procedure too. You know, that kind of the important thing is that we don't actually always know what the right basis is to measure. And actually one way of understanding the error correction is that it allows us to kind of like rotate the system in an RG sense into the basis, where we know the signal is what we want. Yeah.
Yeah, thanks.
Yep, thanks for the question. Okay, any other questions or should I keep going?
Sorry, what exactly do you mean here by the closed loops being non-zero?
Okay, that's a good question actually, and it's because I was being a little bit sloppy on this slide, and actually we'll get to this in the next slide. So they're non-zero in like a very weak sense. So let me, okay. So, okay, thanks for the question, Arkin, because next we're going to talk specifically about the long closed loops within the topological phase. So, you know, also related to the other question, if we apply small amounts of hx and hc, we can think about this as like there's actually some theorems that tell us that these small perturbations adiabatically deform the ground state. So they adiabatically deform the ground state and introduce a finite density of like short range open strings. And as a result, if we were to measure just like the bare Wilson loop operator, which is like a long Z string, then anytime it intersects with one of these short open strings of the opposite type, it's going to pick up a -1 sign because of the non-trivial mutual statistics between the E anyons and the M anyons. And because the number of places where it could intersect with these short range open strings grows with the perimeter of the loop, we actually in general expect that these bare Wilson loop operators within the topological phase will decay with some perimeter law type behavior. E to the minus alpha L, where L depends on the perimeter of the loop. However, this fact that all of the states within the topological phase are connected adiabatically tells us that if we were able to do some basis rotation, we might actually be able to measure like the original Wilson loop, the one that lives at the fixed point with no fields, now just rotated into the right basis. And it's this original Wilson loop that's like the true Wilson loop of the phase. And this one actually has no decay with loop size. So this remains order 1, or as a loop size becomes arbitrarily large. So, you know, there's this nice paper from Hastings and Wen where they actually discuss this in great detail, and there they call it a zero law for these like true Wilson loop operators. So the procedure that we're going to outline today doesn't actually construct this adiabatic connection. However, it still is able to asymptotically achieve some order 1 type scaling, a zero law, in the vicinity of the topological fixed point. So that's kind of like the key advantage of using this error detection property in order to classify topological phases. it allows us to turn this perimeter law into something that's effectively like order 1. Okay, so questions about this? Okay.
So here, what decays exponentially is just the expectation value of the Wilson loop operator with respect to this perturb ground state, or
Exactly.
Okay.
Exactly right. Yeah.
And
the
can
expectation.
you give intuition for why it's exponential and not just polynomial in the perimeter?
Yeah, so the way I like to think about it is that for every unit length of the loop, there's like some probability that it's going to that there's going to be a virtual fluctuation supported on
Okay.
that side.
Yeah.
And
Right.
so the chance of this expectation value remaining 1 decays exponentially with the number of locations where an error could occur.
Okay, got it. Makes sense.
Yeah, and so other people have also discussed like detecting topological order in generic phases or generic points in the phase diagram. One of the approaches is to measure the topological entanglement entropy. This is a basis-independent quantity. However, one of the issues with topological entanglement entropy is that it's actually like exponentially small. You're trying to measure the entropy of a large region, and therefore this approach actually has very high sample complexity. People have also tried to characterize topological order by using disorder parameters. Essentially, here you detect topological order by measuring the absence of order. However, actually, we'll see that in the case of mixed states, these disorder parameters don't actually make sense anymore. Because when you have mixed states, there's many different ways in which you can have no apparent order. For example, a maximally mixed state. Now, people have also directly tried to identify this adiabatic change of basis, this basis transformation, using like variational type approaches. In particular, people have tried to use tensor network approaches to optimize matrix product operators. And these are actually quite interesting. But again, in a real experimental setting, it's not so clear how to do this actually from data. Typically, they do this numerically using tensor network, like using a tensor network representation for the true state. So the approach that we're going to kind of discuss today is an extension of some prior work, and in particular, we were inspired by this QCNN work. So Iris actually is also, kind of like my co-conspirator on this project. And so we essentially use the key ideas of that paper, which is to generate, use essentially ideas of like error correction to generate an RG flow towards the fixed point. And by flowing the system towards the fixed point, that's another way of amplifying the like Wilson loop operators. Okay, so with that background, let's actually go through and try to understand what do we mean when we say that we're going to use error correction to flow the state in order to implement RG. So the simple example to think about is the toric code model. So the toric code is a little bit like a 1D version of the Ising of the sorry. We're going to look at the Ising model, which is like a 1D version of the toric code, which has like ZZ operators connecting two sites and then an X transverse field. So if you go into the regime where G is very small, then you kind of have like a symmetry broken state where spins are going to be kind of like polarized, aligned along Z. So the typical order parameter that people use to measure order in the symmetry broken state is like the magnetization. So you essentially measure the polarization of the Z spins, and the presence of this G term causes some sites to be flipped. So a small number of sites will be flipped, but it causes some sites to be flipped. And in particular, anytime you see a site flipped, the way that you can interpret this is that there's like a pair of domain walls that's been created on the sites, the links adjacent to the site that was flipped. And in order to essentially correct for the small fluctuation coming from the transverse field, you can look for domain walls and try to pair them up. So here we paired up like a distance 1 error, a pair of domain walls that were distance 1 apart, in order to restore this spin from down to up. Another way of saying this is like majority vote. So if you look kind of at a region of the system, by taking like a majority vote, you can push errors off. You can remove errors and pair up domain walls and kind of try to restore the original spin. So this is the error correction step, where you do this like local pairing procedure in order to identify and correct spins flipped by the perturbation. And then once you do that, you can coarse grain the lattice, and then repeat the procedure. And the important part of coarse graining is that it takes an error, which maybe is like distance 2 or distance 3 apart, and turns it into a pair of errors that are like a smaller distance apart now. So once we've done the coarse graining, we can remove this error by pushing it to the boundary, and now we only have to flip one spin in order to push it to the boundary after the coarse graining. So the idea is to do this procedure iteratively, d times, and once we do that d times, eventually we're going to flow to like the fully polarized state, as long as we're in the symmetry broken phase. So this is actually also the same as like block renormalization, Kadanoff block renormalization in the context of the Ising model. Okay, so we can generalize this to the setting of the toric code. So just like before, as we've been discussing, fluctuations in the ground state due to perturbations look like errors that are only a few sites apart. So these are like low weight errors. And by applying some local error correction procedure, we first pair up these errors, and then we remove them from the system after we've paired them up. Once we do that, we coarse grain the lattice. So before a distance 2 error is now becomes a distance 1 error, and then we repeat the procedure. So just like in the Ising model case, by doing this procedure iteratively, you can flow the system towards the low density topological fixed point. And once you do that, you measure the Wilson loop in the low density state. And now, because the system has a very low density of anyons, ideally 0, if you're in the topological phase, then you measure like a large expectation value of this Wilson. A nice interpretation of this measurement that we've done involves using like a Heisenberg type picture, where we're actually measuring like a dressed Wilson loop in the original state. So you can kind of think about this dressed Wilson loop as being constructed by inverting this error correction procedure. So it's kind of like thinking in a Heisenberg picture, where the locality of the operation kind of determines how much this Wilson loop gets thickened during each of these inverse steps. So if we do like distance 1 pairing during this step, then we have to thicken this Wilson loop by like distance 1 in the reverse step. So another way of interpreting this procedure is that we're measuring coarse grained Wilson loops on the original state. And you can see now kind of the qualitative connection to these original adiabatically dressed operators, which Hastings and Wen told us are 0, also obey they kind of grow and remain constant even as you increase the size of the loop. These error decorated Wilson loop operators also have very, very slow decay as you increase the size of the loop. They're also essentially order 1. Okay, so that's kind of the procedure that we're going to be studying. So are there any questions on this?
Sorry, this is a dumb question, but for the intuition where I'm not in the correct phase, what should I picture happening as I coarse grain again and again? What do I get on I guess the right-hand side of this picture if I'm not in the topological phase?
Okay, that's an amazing question. And I think the way to think about it, the way I think about it, is actually, so I know you guys are there's some error correction expertise in your group. So you can almost think about the threshold of your decoding operation, right? So if you are not in the topological phase, you're not going to be able to correct enough errors to outcompete the increase in the density of errors coming from coarse graining. So coarse graining like reduces the distance of errors, but it also increases the density of errors. So there's kind of this competition between the rate at which you're removing errors and the rate at which you're increasing the density of errors. And our claim is that you can only win this game, remove all the errors successfully, if you're in the topological phase. And key to that like claim being true is the fact that we're only doing local error correction here. So if you for example, did like a full minimum weight perfect matching on the initial snapshot, you could of course remove all of the errors, no matter what the error density is. But that involves doing non-local processing of information. So in order for this competition to be meaningful, we need to actually restrict the decoding step to only involve local operations.
Cool, thanks.
Yeah, thanks for the question.
So sorry, I had a question as well, and maybe maybe I zoned out at the wrong moment, but so error correction, so the decoding step of error correction is typically sort of a global operation that uses information kind of everywhere. So what is it here that is constraining it to be local? Is it that you're only allowed to measure stabilizers in this narrow region around the ribbon? Is that, I mean, yeah, I'm just wondering, what is it that makes the error correction here local as opposed to global? Yeah,
so that is a really good question. And it's actually because of the way that we construct our decoder. So you can almost think about, so the simplest decoder here involves applying the following rule to the syndromes. Basically, along each link, check to see if both neighboring vertices are occupied by an anion. And if that's true, flip that link. So you can do this like distance one pairing procedure using only local information. You actually don't need to do any non-local communication.
Right.
You can actually like also implement this as like a local unitary transformation by also introducing like local ancilla qubits. Yeah. So we actually like construct our error correction very carefully to make sure that we don't do any non-local processing of information. Does that kind of make sense?
Yeah, I think so. Yeah, so so it's like you've basically fixed a constant distance over which you would match syndromes, and you just don't even look at distances that are larger than that.
Exactly. And when we make the decision about whether to match two anions, we also only take into account the syndrome in the vicinity of the region that we are like making the decision on.
Yeah, so that's a procedure that wouldn't, against a Pauli error model, that procedure wouldn't have a threshold. But I suppose here it's good enough to correct.
So it's kind of, yeah, so that's also a very good point. And we'll kind of see this a little bit later, but when you add the coarse graining step, you actually do recover a threshold under like a simple IID Pauli error model, because at the next layer, when you increase the layer, like if you look at the second layer, now you're effectively like doing the decoding at like a higher distance, like distance 2. That's twice as big. And then at the next layer, you'd be doing it at like, like distance 4, like again, twice as big.
Oh, right.
Yeah. So you still do get a threshold, but it's actually suboptimal because it's not a great decoder.
Right.
But in terms of, yeah, so it's not a great decoder, but it is like, in terms of certifying topological order, it is like a kind of a rigorous approach to.
So, but then I come back to my global local thing, right? So this coarse graining, like you could coarse grain to the point that you only had a single qubit, right? And that would be the complete decoder, but that you wouldn't have any ribbon to measure anymore. So somehow, is it the case, there's some rule here that you coarse grain, like that ribbon still needs to have a length that grows as you grow the system size, even after however many coarse graining steps you're allowing.
Exactly. Exactly. And actually, the most concise way of stating this condition is that this coarse-grained loop operator needs to have an interior. For it to be like a good like Wilson loop, the size of the loop should be much larger than the amount it's being spread by the decoding. Yeah, exactly.
And the size of the loop is not just the length of it, it's also how fat I've made it to. Is that correct?
Yeah.
The area of that like light blue region needs to be much bigger than the white that you've remained.
Yeah,
Oh,
actually, I think it's
yeah,
the other way around.
Yeah,
Where you
yeah,
want
yeah.
you want the white region to be large, so that basically, like, there's no way you can accidentally pair an anion inside the white region to an anion outside the white region.
Right.
So if you had like unpaired anions in the system, if there were anions condensed in the system, then there's no way this loop would be non-zero. Yeah, that's kind of intuitively how to understand why it's like a rigorous procedure.
Can I ask a question while we're on the slide?
Of course.
So in this error correction, are you doing it all in like a unitary controlled way, or are you actually measuring things and then doing the correction incoherently?
Yeah, okay. So also a really good question. We are envisioning using this in like, we show that we can do this. We did this on some experimental data that we have. So in this kind of experimental setting, we actually like here just process a snapshot. So we like took a picture of the experiment, and then from that picture, we compute, all of the vertices where the parity is odd. And then by doing processing of that snapshot, we can like compute essentially the expectation value of this corrected Wilson loop. And then we do that in like the Z basis, and then we also do that in the X basis. And using that, we can like efficiently analyze an experiment. Now, in principle, you can also implement this procedure unitarily. And there's like a few reasons why you would do that. One is if you don't already know the basis in which the stabilizers are. Like when you implement this procedure unitarily, you can imagine like doing some variational optimization of the unitary transformation in order to try to like amplify the signal and identify the right basis to measure in. We also like thought a little bit about like non-abelian topological orders, and there actually it turns out that you don't have this nice property that you can just like measure and then turn it into a bunch of classical post-processing. There you would really need to actually do the physical unitary operations in order to like process the anions and pair them up. But these are kind of like two cases that are a little bit more complicated than the basic toric code. So if we do talk about them, it'll be a little bit at the end. Yeah.
Cool, thanks.
Yeah, thanks for the question. Okay, any other questions? Cool. So this is, I think, the most important slide in the talk. So we can now kind of understand and just like test it out and see how it works in some cases. So the key metric that's going to tell us whether we're in a topological state or a trivial state is essentially the flow of the expectation value of these Wilson loops under this kind of LED coarse graining approach. And as we discussed, the key metric to make sure you're preserving is that the loop length remains a lot larger than the correction distance, so that these effective anions have an interior. Now, we study extensively this kind of like simple perturbed state where we take like the toric code fixed point state and add some, imaginary time evolution by transverse and longitudinal fields. And actually what's nice about this is that it's still like a bond dimension 2 PEPs, so we can do numerics on very large systems here to simulate sampling. And we apply the procedure where, as a function of gx. So there's a phase transition in this model as you increase the size of gx. And by looking at like a sequence of loops where we both grow the size of the loop, and because we're doing this error correction procedure and coarse graining procedure, we're also growing the effective kind of correction distance of the coarse grain loop. We see that deep in the topological phase, these loops kind of rapidly flow and saturate to 1. So these are like indicated by the lines going from light to dark deep in the topological phase. However, in the paramagnet phase, we see that these expectation values essentially remain like uniformly close to 0. I'll also highlight actually this point right here where you see the trends going in the wrong direction. So this is actually related to this threshold comment that I made earlier, which is that this witness, this procedure for classifying topological order, I mentioned that it can't be fooled. So it's a good witness for topological order, but sometimes it'll classify trivial states or topological states as trivial. And this is actually kind of a fundamental thing because, and yeah, if you're actually kind of curious about this, I can explain a little bit more. But yeah, we're not actually trying to like get the phase boundary right. We're only trying to construct a witness for a larger region of the topological phase. Okay, so here I was looking at Z closed loops, the Wilson loops. We can also look at the disorder parameters, which are the open loops. And we actually also see that the disorder parameters get amplified in the trivial phase. And almost by definition in the topological phase, these disorder parameters also are heavily suppressed. So you can see that these transformations are kind of behaving on the state as expected. We can do this for a much larger region of the phase diagram, where now we look at this as a function of both gx and gz. This kind of like gray line here essentially represents the phase boundary. And you can see actually the kind of the main advantage of this approach, which is that in the original model, there's a very small region here near the fixed point state where you can like very confidently classify your system as topological, where the signal is very close to 1. However, using this approach, there's a much larger region of the phase space, which you can very confidently classify as topological. So that's kind of like, you know, this is kind of the region where we're, you know, quote unquote, below the decoding threshold, and the decoding threshold of our RG decoder. And you can use this as a good classification tool or verification tool. Okay, so that was kind of like the initial demonstration of this. Now let's get to some of the more challenging applications. One of the things that's super important if you want to do this in a real experiment is understanding how incoherent errors affect things too. So what we did is we applied like a finite rate of bit flip errors and phase flip errors to our measured signal, and again measured like the Z closed loops and the Z open loops as a function of the error rate as in a function of loop size. So typically, actually, when people like were trying to measure and characterize this topological order, what they would look at is the ratio of open loops to closed loops. So when you're in the paramagnet phase, you see that this ratio is like close to 1. The open loop, this red curve here, and this red curve, and the closed loop, this red curve here, kind of have the same behavior. This comes from the fact that all of the order is in the open loop degree of freedom, in the open loop observable. In contrast, in the topological states, only the closed loop is non-zero, while the corresponding open loop is very close to 0. This is because there's kind of a large energy penalty associated with creating anyons in the topological phase. And this is kind of significantly larger than the perimeter law decay coming from, you know, virtual anyon fluctuations in the topological phase. However, if we now look at this like this phase in the presence of disorder or, you know, incoherent errors, we see that the signature in terms of open and closed loops looks a lot like in the topological phase. In particular, for like a low but finite error rate above the threshold, where we know that there shouldn't be any topological order anymore, we see that the disorder loops still have much larger signal in the closed versus open observables. And so as a result, you know, we're kind of see that in practice, the disorder parameter doesn't work well in the presence of incoherent noise. In contrast, the error correction-based approach actually does allow us to make statements, confident statements about the topological order in the presence of incoherent noise as well. And in particular, we see that if we look at this kind of mixed state phase diagram, where we apply both bit flip errors and coherent perturbations, again, there's a large region near the topological fixed point where we can very accurately classify the state as topological. Okay, so any kind of questions about the effective bit flip, phase flip errors, and actually why the LED error correction approach provides some advantage over disorder parameters?
Sorry, just a very quick question about the behavior of the expectation values of the opens operators.
Yeah.
So there you have to make sure that the opens operators do not span the entire lattice, right? So this is only true if you have like a Z operator that's smaller than the lattice size, right?
Yes, that's right. Yeah. So you can think about all these Z operators as being like less than half of the size of the system. Yeah. Yeah, that's exactly right. Actually, the systems that we looked at were pretty large because we were using some PEP sampling techniques in order to do our numerics. So yeah, that's how we can go to like very large loops without worrying about system size effects. Yeah. Okay, so the key thing that allows us to distinguish between these two phases, the one with like low bit flip error rates and the one with high bit flip error rates, I think from a physics standpoint, it's actually like not so clear exactly what changes, when you go from one of these regions to the other. However, from like a quantum computing error correction standpoint, it's actually very clear. It's that in one phase, if you do error correction, error correction can succeed, and in the other phase, error correction can't succeed. And actually, by using kind of local error corrected Wilson loops as like the bridge between these two, we actually see that this ability to do the correction of like a Wilson loop tells us something about like like whether or not like zero law Wilson loop even exists in this phase. And so we kind of are distinguishing between these two different phases, these two different kinds of perimeter laws, by like really emphasizing whether or not they're correctable or uncorrectable. And this is something that is unique to this approach that also applies to like the mixed state case. Now, of course, there's some like kind of interesting open questions here, which our work leaves unresolved. First is that the boundary of this region is very decoder dependent. So if we try different decoders, we actually get slightly different boundaries, which kind of begs the question of like, is there an optimal version of this procedure where we show that we've like saturated the local decoding threshold in some way? Okay, so another interesting regime to consider is finite temperature. At finite temperature, there's no topological order, and this is also relevant in experimental settings where people do, say, finite time adiabatic ramps, where you also don't expect any long-range topological order. And these effects are kind of reflected based on non-monotonicity of the flow. So here we have some rate of local errors and also some rate of finite temperature. And we see that at short layers, at low layers, we can remove these local errors and therefore amplify the signal. But in the presence of small but finite temperature, eventually when we go to a large enough length scale, the signal will turn around. And the reason is that when you have small but finite temperature, you have initially a very low density of very distant anyons. So these are uncorrectable anyons that don't come with a pair. And as we kind of mentioned under coarse graining, the density of these uncorrectable anyons starts to build up. So it's only when you go to a very high layer in your LED that you're able to observe this kind of buildup of this low density of uncorrectable anyons. Okay, great. So next I'll kind of go to this experimental application, which I promised. So the experimental setting that we'll think about is actually a dimer model. So the experiment that we have in our lab here is an array of Rydberg atoms. And these Rydberg atoms interact with each other via a very strong repulsive interaction. So if you tune your lattice spacing just right, the repulsive interaction can be so strong that if you're occupying the site at the center of this circle here, it essentially prevents occupation of all sites inside this red circle here. Now, by combining this with like a term in the Hamiltonian that energetically prefers Rydberg excitations, you can make it so that the ground state is like a maximally packed configuration, satisfying kind of this constraint over here. And if you can prepare an equal weight superposition over all of these different dimer configurations, then this is an alternative realization of Z2 topological order. So we can apply our procedure to the experimental data. And in particular, the experimental data was taken on a lattice of this size. And the loops that we consider are actually quite large compared to the underlying lattice size. And if we look at this blue line here, sorry, the pictures look actually kind of blurry. It might be a PowerPoint downsampling. But if you look at this blue line here, you see that in the original data, there was no signal in this very large loop. However, if we do like a few layers of our correction, we see that the signal starts to increase, in particular in this like region 3 and region 4. And I'll note that region 3 is the region which is kind of theoretically predicted to host this resonating valence bond spin liquid type phase. We can also apply the equivalent procedure to the open loops. And in the open loops, we don't see any increase in the corresponding expectation value, which also corresponds, is a signature that the system is in a topological phase. We also apply the procedure to the X loops, and this is the X loop we picked. And there we saw kind of large amplification of the closed X loops in this region 2 and also in this region 3. However, when, and actually, here we saw amplification in region 4, but here when we look at the X loops, we don't see amplification in region 4. When we also apply the procedure to the open strings, we see that the signal gets amplified in region 2, but doesn't get amplified as much in region 3. So the way that we can interpret this combination of behaviors is that in region 1, you only amplify the open Z string, which tells you that you have a paramagnet in the Z direction. In region 2, you amplify open X strings and closed X strings, which tells you that you have essentially a paramagnet in the X direction. In region 3, you only amplify the closed strings without also amplifying the open strings, which tells us that we probably have a spin liquid phase there. And then in region 4, where we see the kind of expectation value of the closed X loop stops increasing, we actually think we have a disordered phase. However, this disordered phase is different than the one that was theoretically predicted. Theoretically, it was predicted that this would be a valence bond solid in region 4. However, if this was a valence bond solid, then we should have also observed amplification in the Z strings. Instead, we don't observe any amplification in open Z strings or open X strings. And as a result, we think that this is a disordered phase that's actually dominated by decoherence, as opposed to becoming a valence bond solid. Okay, so any questions about experimental results?
Yeah. So what's the x-axis? What are delta and omega experimentally in terms of the Rydberg?
Okay, yeah, good question. So sorry, I forgot to mention this. Delta is essentially a term that preferentially tries to place Rydberg excitations into the system. So I mentioned this kind of like maximal packing problem here. When delta is negative, actually you end up in the state where you have no Rydberg excitations. And then when delta is large and positive, this prefers putting Rydbergs into the system. Omega is the coefficient of the flip-flop term, or the spin flip term, which allows you to create and remove Rydbergs from the system. So it's the thing which generates kind of the quantum fluctuations. Yeah.
Okay. Sorry, go on.
So the reason the spin liquid phase kind of arises at this intermediate value is that this is when the two things are perfectly balanced. So you have enough omega in the system that you can coherently move from one spin configuration to another, like one dimer configuration to another. But it's, delta also needs, so if delta gets too big, then these like spin flip processes go away. These resonating ring exchange terms go away. But if delta is too small, then you don't actually you don't have enough maximal packing in the system to like favor dimer states over, say, just like a, X paramagnet, all Rydbergs fluctuating equally type state. So that's kind of why this spin liquid only appears in like the intermediate regime.
My other question was, how do you know that your the successive layers of LED at say d equals 2 isn't just like a spurious like little peak like you showed in the last slide, where if I keep doing that layers, I will get back to like 0? Like,
okay, that's a fantastic question. And at the end of the day, it's all about kind of length scales. So, the reason why the signal became non-monotonic is that because of the finite temperature, when you went to really, really long length scales, you actually did lose your long range ordering. However, our experiment is only about this big. So it doesn't actually make sense to think about like length scale as much beyond the regime of this experiment. The experiment was also prepared in finite time, right? So, the amount of time it took to prepare the experiment also sets a limit on like the length scale up to which you can certify your topological order. So, roughly speaking, I think the conclusion that we would say is that this signal shows that there are signatures of topological ordering up to this length scale, which tells us that, if we do have a resonating valence bond state, which it looks like we do, the resonances, the long range entanglement seems to persist at least up to this large length scale. Yeah, but we don't make any statements about like L goes to infinity. We kind of can't on experimental data.
And this is just a really dumb, simple question. Why didn't I just do the Z loop around the entire thing? Why half the system?
That is also a good question. And from a practical perspective, this is kind of as big a loop as we were able to do, while still getting something that looked reasonable. So if we actually like add another chunk to the system here, the signal gets quite a bit worse. Yeah.
Oh, so those atoms aren't even like participating in this, or like all the action is like on this bottom half of the system. Is that what you're saying?
Oh, well, we average over all loops of this size.
Oh, okay.
Yeah.
Right.
But what I'm saying is that if I made the loop even bigger, then even this increase like would have disappeared. Yeah. So whether that's like whether that's like a reflection of some correlations in the underlying state, or just like, the noise kind of just was too much for that particular loop, we're actually not so sure. Yeah. This is kind of the biggest loop we were able to do.
Cool.
Yeah. Thanks for the question. Any more questions? Okay. If not, I will trudge along. So the last thing I want to talk about a little bit is like some more theoretical aspects of the work, and also some of the generalizations which we've been pursuing. So first, I kind of want to we've kind of been discussing this, so it should be somewhat intuitive, but I want to make kind of explicit the connection between these decorated Wilson loops and like a surface code. So you can think about this like region around the like original Wilson loop as also being a surface code. And you can imagine trying to do error correction on the surface code. And in particular, it's like a distance 2D surface code. And if the surface code has like no anyons in the interior, then this means that when you like apply a Z loop that connects the interior to the exterior, it has like expectation value +1, which tells you that the surface code is in like the 0 logical state. So like 0 logical state of the surface code is equivalent to no anyon on the inside. And then these two different forms of error, which can destroy the topological order, incoherent errors, high rate of incoherent errors, and coherent errors, essentially correspond to two different types of excitations. So the incoherent errors are like a high density of very short range correlation, short range errors, like single site bit flips. But then these coherent errors, which come from like increasing your GX, also can kind of deposit like long range correlated errors on your surface code. So these are kind of like the two different types of processes which can destroy the signal in the surface code. And in particular, once the signal becomes too noisy, the system becomes uncorrectable from the point of view of the surface code. And then from the point of view of the entire topological system, not just near the ring, this corresponds to like loss of long-range topological order. Yeah, okay, and this is kind of what I was saying. You can have long open strings and short open and high density of short open strings. We can also construct this type of procedure as like a unitary quantum circuit if we introduce ancillas. And the key idea is that you can actually use unitary operations in order to simulate local error correction. So if we go back to the Ising model case, because that one's just a lot simpler, what you can do is you can introduce one layer of unitaries, which essentially measure your stabilizers. And in the interest of time, we don't have to like think carefully about the specific circuits, but just take it for granted that this blue part here measures the stabilizers. And then once you've measured the stabilizers, you can apply another logic gate, controlled not gate, to essentially simulate majority vote. So another way of thinking about this is that you measure like the location of two anyons, and if both anion sites are occupied, then you flip the spin in the middle. And this is something you can do entirely using like coherent unitary operations. So what this tells us is that there's some pretty complicated circuit which can realize this procedure, and this dressing of the operators, this Heisenberg picture dressing that I mentioned, essentially corresponds to pushing operators through these unitaries, conjugating them on both sides and effectively growing their size. And indeed, it's the locality of the operations which guarantees that this fattened operator or coarsened operator remains local. So this is also why like locality of the information processing was important, because that's what allows us to encode this as like a local unitary circuit with the processing replaced by classical logic gates. So the other kind of like theoretical result which we kind of fleshed out was to show that if we are able to measure large Wilson loops after doing this local unitary procedure, then this tells us that we have non-trivial order in the input state. And in particular, we prove these two results in the methods of our paper. The first is showing that if you measure these stabilizers after correction to all be exactly 1, then you can't have like a product state, which like actually realizes, which like would be processed by this local unitary circuit and ancillas in order to produce like the toric code state out here. If you put in a product state here, you just couldn't get out the toric code state there. Then we also prove kind of like an approximate version of this result, where we assume that in the output state, we can only approximately measure Wilson loops close to 1. So like Wilson loops are actually like 1 minus epsilon. And we show that the size of this epsilon leads to kind of a length scale up to which we can certify the topological order. So in particular, if we measure Wilson loops of like 1 minus epsilon up here, then this tells us that no state with correlations smaller than inverse epsilon minus d would be able to be inserted here and give us like this topological state up there. Yeah, and actually, so Arkin also actually like worked out some very similar proofs in his paper too, which was posted around the same time. Yeah, so if you have questions on the proof techniques, of course, I'm happy to talk about it, but also you can ask Arkin. Yeah, so and kind of more from the physics side, we kind of are thinking about this ability to take an input state and apply some local unitary circuit in order to prepare like a toric code state on a subset of the qubits as actually a possible like way of defining or characterizing mixed state topological order. It's this ability to kind of like locally distill long range entanglement from a state that could tell us whether it's topological or not. And this type of definition applies both for mixed states and for pure states. Okay, great. So this is kind of some of like the theoretical implications. Actually, some new results that we've been working out are also trying to explicitly connect this local error correction procedure to like the entanglement negativity, which is a version of it's like a version of entanglement that also is defined for mixed states that people have been studying in the concept of mixed state topological order. And in particular, we are able to show that if LED flows to 1, then this implies something about the entanglement negativity in kind of a, with some like strong additional assumptions that aren't physically satisfied in our setting, but are still like plausible. And so we kind of conjecture that this is probably true in general, but we just weren't able to prove that it was true in the more general case. So the first kind of assumption is that when you apply this LED procedure to a mixed state and inserting pure state ancillas, you get out a pure toric code state here, but then some mixed state on the ancillas. You move the entropy from the system to the ancillas. If these ancillas don't contain any long-range correlations, then we could actually have prepared this ancilla mixed state by taking a product state and applying a local unitary circuit to it, and then tracing out some degrees of freedom. So in other words, this mixed state here would have like a local purification. So there's some local circuit which can prepare this mixed state here. And this tells us there's no long-range correlations in that part of the mixed state. Then, because this LED circuit down here is also local, this tells us that we have a local circuit which connects this stabilizer state up here, so with long-range correlations in the toric code part, and then like trivial correlations on the remaining degrees of freedom, connected by a local unitary circuit to the input state, which we are trying to rigorously certify. And in particular, if we further assume that these unitaries are Clifford circuits, so this is like the step where this is mostly just for proof convenience. If we assume that these unitaries are Clifford circuits, then we can actually go ahead and show that the topological entanglement negativity on this state down here must have a topological term as well. And kind of the key intuition is that by always kind of coarse graining and taking like large products of stabilizers, you can construct coarse grain stabilizers which have non-trivial twist product, even if they're kind of dressed by these like local Clifford unitary rotations. Yeah, so these are kind of some new results which hopefully we'll post on arXiv soon. So okay, any questions about this one? All right, and I guess in the interest of time, I'll keep moving. We also kind of worked out a generalization of the procedure to non-abelian states. In particular, we were thinking about like, non-abelian like quantum doubles or like string net type models. And actually most of the key ideas carry over to these settings too. So now we want to think in the circuit setting, where we first kind of measure local anion content using like some controlled perturbation between the system and the ancilla. Actually constructing this perturbation in terms of circuits is kind of tricky, but these perturbations do exist. These projections do exist in general. So this is kind of the analog of like measuring a stabilizer. Now, step 2 is actually another step where things kind of change. Here, when we try to do our error correction or our pairing procedure, there's only some probability that the pairing procedure will actually fuse to the vacuum. So the way that we decide whether to pair up anions is like, if these anions could in principle fuse to the vacuum, then let's try to pair them up. However, sometimes, because of, with some probability that depends on the structure of the underlying unknown state, you might actually fuse into like a different superselection sector. And this kind of comes from the fact that these are non-abelian anions as opposed to abelian anions. So, this pairing is probabilistic, so you can try repeating it multiple times in order to, maximize the number of fusion outcomes that you get in one. But eventually you're going to have to stop trying to pair anions because it's not going to help anymore, and then do another coarse graining step. And actually, for coarse graining, people have discussed using, there's essentially a Mira type circuit for non-abelian models, which you can also use for this step. And you iterate these steps 2 and 3, steps 1, 2, and 3 many times until you ultimately measure, the S matrix of your topological theory. So this S matrix is essentially the generalized, braiding operation between pairs of anion types in the procedure. In the toric code case, these are like the E and the M anions. And if you measure this type of observable, you would have measured like a -1 phase. In more general anion theories, the object which describes all of these interrelations is the S matrix. And it's one of the things that allows you to characterize that you're in the right topological phase. Yeah. So these are also some like new results, which will also be included in the next archive posting. Okay.
Sorry,
and
before you move on from that one, so that's really interesting. And I think I would have guessed that you need post-selection to measure the S matrix, but can you say something about that finite probability? I mean, is it constant as you make the strings long? Like what? Yeah.
Yeah. Okay, good. So this is a really good question. And so the way that we are kind of imagining or envisioning proposing this S matrix or measuring this S matrix is to kind of, in an ancilla controlled way, create these pairs of anions. So like an AAA bar and AAA bar, and then braid them around each other. Now, because these are non-abelian anions, when we try to refuse them at the end, there's only a constant probability that they're going to refuse to vacuum. And if they refuse to something else, then there might be ways of getting around that, and like trying to figure out what it fused to and correcting it. But the simplest thing to do, which we know works, is to just try again and keep doing it until you get an event where the anions fuse to vacuum. So indeed, it should be like some finite probability, like because this fusion event is coming from anions that we created ourselves. It should be like something that scales inversely with the quantum dimension of underlying non-abelian anions. Yeah.
So, but what about, okay, so that all makes sense. But I suppose my other question is, what about the operation of moving the non-abelian anion itself? So, in the abelian case, those ribbon operators are kind of they're unitary. You can implement them with probability 1. I'm not sure that's true in the non-abelian case in general, that you can actually just implement the motion with probability 1.
Yeah, so my understanding, at least for like simple like quantum doubles, I say simple for like quantum doubles, is that there's still like a finite depth circuit which can be used to move these anions. So like, at least for me, one way I like to think about this is like, there's like, you could imagine using like an adiabatic procedure, where you, energetically, create like some energy penalty and like move that around in order to have the anion follow it. And people have like constructed, there's like these I think there's these circuit constructions where you can also like apply a finite depth circuit in order to move the anions around.
So do you mean a finite depth adaptive circuit, or I thought for non-abelian anions you need a linear depth circuit in the distance you're trying to move it over if it's non-abelian?
Yes. I meant to say linear circuit. Yeah. Okay. Sorry.
Yep.
Yeah. Like a circuit where you like apply something on one site and then you apply it on the next and then the next and the next and the next. Yeah. Which is in contrast to the abelian case. Exactly. Yeah, you're exactly right. Where you can do this whole thing using like a product of local unitary rotations. So something that doesn't actually like physically move an anion.
Right. And then that should be allowed. Yeah. Okay.
Yeah, exactly. Sorry, linear depth circuit. Sorry, that's the word is. It's 10:30 here. My brain's fried.
I actually also have a question that is like related to that, because were you guys able to somehow generalize the circuit depth lower bound also to this setting? Because we were really struggling to do that because of the very same reason that essentially the upper bound on the twist correlator is a function of the depth of the Wilson loop operators, and you would need that to be a constant. So the fact that for non-abelian models you don't have Wilson loop operators that are constant depth unitaries, like really didn't allow us to make any progress on that. Did you guys think?
That's a really good question. I haven't really thought about this too much. No. I would imagine actually that because like in our circuit construction, we always require that the pairing distance is constant. Maybe that's actually something helpful when you're trying to think about this, because the pairing distance is always constant, we're never going to apply like a circuit depth that grows with system size as repeated pairing procedure. Yeah.
I see.
Of course, there's like, yeah. There's also, like you might have to do it multiple times, and then at the end you still have to measure the S matrix. So it's definitely like, yeah, quite non-trivial. We haven't thought about this. That's a good question.
Yeah, right.
Yeah. Cool. Okay, any more questions? All right, so I think actually with that, so there's also like a much simpler generalization. You can also think about like other gauge theories in higher dimensions. For example, like 3D and 4D toric codes, where now your pairing procedure could be replaced by something like a loop contraction procedure. This is like another way of trying to generalize this to systems with different types of excitations. Okay, great. And with that, that brings me to the end of what I want to tell you guys about. We talked about, these 4 different kind of contexts, and mixed states, spin liquid experiment. And actually one thing which we're kind of interested in the context of experimental applications is this idea of adaptively selecting the measurement basis in order to handle cases where you don't already know which stabilizers to measure. And also something that I also find kind of like interesting, and I don't really know where to start there, is like also trying to see if there's like an analogous procedure for systems with like continuous symmetries or continuous gauge groups, because there the connection to error correction actually becomes a little bit fuzzier. Yeah, so I think these are also like interesting, cool directions. And to conclude, of course, I very much want to thank my collaborators. So, Iris and I worked on this stuff together for quite a while. And then also Min was a postdoc at MIT. And then these guys are all, actually, Hannes and Sunwon and Julia were all postdocs when this started and are now faculty. And of course, Misha is my PI. So special thanks to Misha and all these people for discussions. And to you guys for your attention. Thank you so much.
Awesome. I think probably asked for enough questions during.
Yeah, that's great. Thanks very much for that. I suspect we asked enough questions. Thanks for putting up with them. It's really great to hear about.
Thanks for asking them. It was a lot of fun.
Yeah, and thanks very much for organizing, Arkin. Great to meet you, Nishad.
Yeah, nice to meet you guys too.
Cheers. All right. See you guys.
Yeah. Thanks, Arkin.
Yeah.